Okay, so today we'll start a new chapter, which is of quantum physics or quantum mechanics. And we'll start by discussing why do we need it? Uh, where did the idea of quantum physics comes from? What makes it different from classical physics, what we'll call them? And, uh, and then we'll get into some of the technical jargon. Right. So let's, I'll start off with this, that everything that we have been doing so far was classical physics. So far, everything we did was classical physics. Right? Starting from kinematics, dynamics, even electricity and magnetism, all of it was classical physics, right? When we discussed oscillations and so on, right? All of that was just classical physics. Sometimes you can also call this as Newtonian physics or Newtonian mechanics. And the punchline here is that everything that we have been doing so far is really not correct, right? It's now when I say it's not correct, I don't mean that it's wrong in its entirety. However, it is not complete, right? So everything that we know in classical physics, it uh, is incomplete. It remains incomplete. It cannot describe a lot of things, right? When we get into the subatomic world, things, classical physics, classical mechanics cannot predict things. So when I say predict things, that's what we do when we do physics, right? We write an equation, we solve it, find its solutions, and those solutions define how will the system evolve dynamically in the future, right? So using classical mechanics on a subatomic scale, you don't get correct answers, right? And so, of course, you need something else. You need new physics at the time, and it was quantum physics, right? Now, this I'll start off with discussing some key features of quantum mechanics. First and foremost, quantum mechanics today is it is approximately 100 years old, right? And we have even better versions or ways. The word is frameworks, but we'll get into that as well, of describing nature. But quantum mechanics was a very big leap from classical mechanics. So, and up to this point, we are still really discovering some of the surprising features of quantum physics, and it still remains the subject of a lot of investigation and speculations as well. Now, I'll come to this idea of a framework. Quantum mechanics is what we call a framework, and it is a very rich and elegant extension of the classical physics framework, right? Of course, you're going to see that this framework of quantum mechanics, it's very counterintuitive and it is almost paradoxical, right? Now, I'll start with the idea of frameworks, right? So let me adjust the zoom, lock it. Okay, so I'll start with the idea of a framework. Okay, so there is a difference between framework and theory, right? So when you started off in the beginning, a steadying motion, we learned kinematics, we did dynamics, and we learned the basics, the equations, the laws, and everything. And then we applied it to the systems, right? For example, we did oscillations, we did electricity and magnetism, and all of the equations, we were still following the same procedures. We had an equation, we found its solutions, and then we could predict what happens. That all of this, this was theory. The framework is the basic idea. For example, Newtonian mechanics, right? Newtonian mechanics was a framework, and a theory is composed of this framework. So the framework can be defined as an object, or well, you can say that it's a picture in which we do physics, right? And there can be many, there are multiple pictures that we can do physics in. The most basic and the most limited one is what is called Newtonian mechanics, right? So we'll start with that. But before, a theory is composed of a framework. So you pick what framework do I want do I want to do physics in, and then you pick. It is also composed of. So I use this symbol. Let's just think of it as and framework, and we call this thing degree of freedom. Degree of freedom. Degree of freedom just means that, again, for example, if I have a particle, I restrict it to move along this line only, right? It can move only along this line. So it has some degree of freedom, and that degree of freedom can be characterized by numbers. And in this case, it is just 1. It has 1 degree of freedom. It can only move in 1 dimension, right? So the degree of freedom, DOF, for this particle is just 1. Suppose I would say that it can move up and down as well, then the degree of freedom becomes 2, right? It has a freedom in moving in 2 dimensions, right? So you need it for to have a theory. For example, gravitational fields, gravity, right? When we talked about gravity in the beginning, that is a theory. It is composed of a framework and degrees of freedom. So the framework in case of gravity that we have done so far was Newtonian mechanics, and the degrees of freedom were basically whatever really polar coordinates, what we call them, right? Your r and theta, right? So you have an object that is moving along a planet. I was supposed to draw a circle. Okay, so this thing moves along a planet, so I can draw a vector from the center of the planet, which is a vector r, and from a horizontal, it will be at some angle theta. So these are polar coordinates, r and theta. So that was our degree of freedom. Now, it turns out that, well, Einstein's general relativity is a theory of gravity, and that is done in a certain framework, right? Instead of following Newtonian mechanics. So gravity is a theory which is composed of a framework and degree of freedom. It was just one example. Now let's move on to different types of frameworks. I'll not get into details of every single one of them. We'll just try to restrict ourselves to quantum physics, right? So I'll start with Newtonian mechanics, the one that we have been doing so far and we are familiar with it. So Newtonian mechanics. Now, these frameworks include what you are dealing with. For what I mean by that is Newtonian mechanics, we deal with particles. So we define a point particle, right? And we have fields as well. So you have both of these things. Fields such as, remember, we talked about electric field, we talked about a gravitational field, right? And a multiple temperature field is also something that we talked about in the very beginning when we were discussing gravity, and so on, right? Now, and you know a lot of things, you know most of the things about Newtonian mechanics, right? So that's the first one. Then we have another one which is called special relativity. I'll write it SR. I'll not go into its details, but it also consists of, it also includes particles and fields, right? And this framework is really important because motion is relative, right? And the fact that speed of light is a constant number. So there is a fixed bound on the speed of light, and so nothing can go faster than the speed of light. But then suppose that you have a car that is moving, and its headlight is on. So the light is moving at speed c, and suppose the car is moving at 60 kilometers per hour. Suppose this is the case. If I were to stand outside and observe the speed of this headlights, classically or Newtonian mechanically, I will say that it should be c plus 60 kilometers per hour. You add the speeds, the speed of the car and the speed of light. For the observer who's standing outside, he'll measure it as 60 plus c. Of course, now this is wrong because it is a postulate, it is a very important law of physics that so far we have this thing that nothing can go faster than the speed of light. Nothing that carries information, right? That's very important. So again, then this was a problem. This is not true. So special relativity, one of the things that it gave us was how do you add velocities? I'm not going to go into its detail, but that's what special relativity was. How do you add velocities so that you can make sure that the velocity does not exceed the speed of light, and obviously it gives you a correct result. Right. Then we have what is our topic is quantum physics or quantum mechanics. I'll call it QM. This quantum mechanics, so special relativity, everything that we talk about in relativity is relativistic. We call it as relativistic mechanics as well sometimes. Now, this quantum mechanics that is part of our course is non-relativistic quantum mechanics. So we will not include special relativity in our discussion. So it is non-relativistic quantum mechanics. Again, this also consists of particles and fields, quantum fields and quantum particles. These particles and fields are different than the particles and fields that we're familiar with. You're familiar with particles as being objects which have zero size, right? They have zero size, and that's how you mathematically define a point, right? A point particle. We'll talk about what particles mean in quantum mechanics, and there are multiple interpretations of this thing of quantum mechanics. The idea of I'll get into is the Bohr's idea. There is a statistical approach to it and a path integral. There is something called path integral, that approach to it as well. But we'll stay with the Bohr's idea. Now, Bohr's idea was this, that so you might say quantum behavior is only restricted to subatomic particles, but that's wrong. The reality is that everything can be studied using quantum mechanics. In fact, the equations that we have in quantum mechanics are more general compared to the Newtonian mechanics equations. So Bohr's idea was that quantum mechanics is indeed true for large systems as well, not only subatomic particles, but for large systems as well. However, the discreteness, and I'll talk what that means, the discreteness is very small, or relatively small. So we'll talk what discreteness means in detail, but at the moment, it just means that energies are discrete when we are doing quantum mechanics, right? So there's not a continuous spectrum of energies. There are some discrete specific energies. It is E equals to NH nu, where this nu is the frequency, H is Planck's constant, and N is an integer which can take integer values. So this makes sure that it's discrete. Well, we'll talk about this equation later. Now, you're familiar with this one thing that was from oscillations. You're familiar with what is a simple harmonic oscillator, right? So what was the energy that we studied in oscillations of a simple harmonic oscillator? It was 1/2 mass times omega squared times the amplitude, x naught, or let's call it A, amplitude, right? Now, quantum mechanics, so this is in classical mechanics, I'll say CM, and then quantum mechanically, we'll not go where we get this equation from, but the energy of an oscillator, or there is a quantum mechanical version of a simple harmonic oscillator, right? I might have mentioned this before, that the subatomic nature of particles, that there are solids that are we say that solids are made up of particles which are just vibrating at their positions. That vibrations can be modeled as simple harmonic motions, right? An oscillator that is oscillating simple harmonically, but those are the particles. So the equation, the energy for that is N plus 1/2 times H cut omega. Again, this H cut is what we call Planck's constant. It is a reduced Planck's constant. You don't have to worry about it right now, but this is the energy. And if I choose a system, a classical system, suppose it has a mass of 1 kilograms. I'm just considering any oscillator with a mass of 1 kilogram, frequency of 1 hertz, and an amplitude of 1 meters. So if the amplitude is 1 meters, it is really a classical system. Even the mass is 1 kilograms. That makes sure that it is a classical system, a large system, right? Not a subatomic particle system. When you put in these values in these equations, right? For a classical system, N is of the order 10 raised to power 23, right? The Avogadro's constant, the number of particles. And once you do these calculations and you want to see the discreteness of energies, it is delta E by E. And you take this ratio, and this ratio is approximately very close to 0. It is 0.00000, something like that. So that's where you see that for the classical systems, the discreteness becomes very small. But the real thing is still that there is quantum mechanics is the more general version of things. Now, finally, I'll sum this up with the final one is quantum field theory, right? And this is the most recent one. This is the most precise understanding that we have of nature today. And it is in this framework of quantum field theory. In quantum field theory, I'll not go into details, but there are only fields, no particles, right? There is no such thing as particles. There is only fields, and what we call particles are just excitation in those fields. What do I mean by that? Suppose I have a field. This is let me draw it again. Well, it is supposed to make a rectangle, but it's not. Anyways, this is a field, and in this field, well, at the point, it's empty space, but there are some, you can say, these waves, right? There are a lot of waves in here. So wherever you see that there are peaks in the wave, those are the excitations in the field, and at those peaks you will be seeing particles, right? So whenever you disturb a field, it creates a particle out of it. So that's quantum field theory, and it is I'll not go into any more details, but it is the most precise understanding that we have of nature today. Let's move a bit forward, and let me go to the next page. So quantum physics has basically replaced classical physics completely as a correct description, a correct fundamental description of our universe, right? And it is used to describe most phenomena that occur at short distances, and it is we also we have this thing, as I told you, that quantum physics or quantum mechanics is just a framework. You use it and you can apply it to theories, right? Theories like electrodynamic, or let's call it electromagnetism, right? Electricity and magnetism, which is given a name electrodynamics, right? And when you apply it to electrodynamics, electricity and magnetism, you get something that is called quantum electrodynamics, and it's a whole new subject. And then you can apply it to light or waves or optical devices, any kind of optics. Then you have something that's called quantum optics, and then you can apply it to gravity as well, and that's where you have a quantum gravity. Now, this the idea of quantum physics began in around 1925, where there were some discoveries by a couple of scientists, Schrödinger, Heisenberg, and the seeds really for these discoveries were basically planted by Max Planck, and Einstein, right? Albert Einstein. And there were more people, Bohr as well, and de Broglie. So I'll write de Broglie as well, because we'll study his, let's call it, law as well. So we'll start by discussing the idea of photons, and what do we mean by a photon? What is a photon, and how is that a quantum particle? So the let's start with this, that a photon. Okay, so the idea is that in quantum mechanics, there are things behave like they're waves and particles, both, right? So it is usually said like this, but the reality of the situation is that it is not particles and not waves. It is something else, but the properties, the behavior of them is sometimes similar to what is called what are particles, and it is sometimes similar to what is called waves. Now, photon is, so we say we have light, right? We have a light and we can see a light all around us. But what is this light? It is made up of little packets of energies, right? So these little packets, so suppose I have this is one packet. Again, I can have multiple, but again, this is not what a photon looks like, but it's something that you can use to help understand. So you see, there are discrete packets of energies, and this is the smallest unit that you can have of those energies. These photons are what you call light, right? So when you shine a laser beam, it is these photons that are part of that beam, right? There's a lot of photons in that beam that are traveling in a particular direction. So this is basically the idea of a photon, and it is it is a quanta. Quanta is basically an indestructible, the smallest unit of something. So in this case, it is a quanta of energy, of the electromagnetic energy. Photon electromagnetism, wherever we were talking about electromagnetism, we talked about the electromagnetic spectrum, where we have radio waves, microwaves, and X-rays, and so on. Visible light was also part of that. All of that is photons, right? So photons have different wavelengths, which means they have different energies. There can be multiple energies for photons, and those energies completely depend on, I can use the word color of light, because we have red, violet, blue, and so on, green, yellow, and all these colors have a particular wavelength, and that wavelength corresponds to the energy of the photon. So in quantum mechanics, there is something that is called, which is a result of this thing, that and light is made up of photons that they're really particles. So the consequence of this is loss of determinism. What does that mean? That means, I'll give you a very simple example. Suppose I have a particle that is sitting over here. So this is my particle just sitting, and how do I see? How do I measure this particle? How do I see what any observation that I want to make on this particle is done by throwing something at it, right? And then in our case, it is light. You shine light, and you can see, you can measure that, okay, the particle is sitting there. Any measurements can be done by observing this. One way of observing something is throwing light at it. So if light is a photon, if I throw a bundle, a packet of energy, we usually draw it in diagrams. We just draw it as this wave and something like this. So I throw a photon at it, right? What happens? What would you expect to happen? A photon is a bundle of energy. So this particle is going to absorb, or the energy from the photon is going to be transferred to this particle. And when that happens, what will happen? If it was sitting stationary, it will move in some direction. Suppose it moves in this direction. What does that mean for determinism? It means that when I throw light at something, when I want to make any measurement on a particle, then I cannot with certainty, I cannot say that it is either moving with this velocity or it is at this position. So just by seeing, by observing, by throwing light at the particle, I changed its position, which can be said as that I changed its state, right? So again, why does that happen? The photon carries energy, and that energy is transferred to the particle when the photon strikes it, and that would cause some momentum change in the particle itself. And when that happens, the particle position changes. So while by measuring a particle, we changed its position, its state, right? So there, determinism is lost in this case. All of this is handled by the idea of probabilities, that we can just say that it is probable that the electron could be there or there or there. And well, yeah, so that's more or less loss of determinism. It is, let me find some wait, no, find some wordings for this. So when you shine light on a particle, it is done by a photon which carries energy, and is transferred to the particle, which changes the state of the particle. Now, it is from this understanding